Mars feels familiar, almost welcoming, but it isn't a good place to visit. It is just the least bad one. Over the years, the real Mars turned out to be far stranger and more dangerous. One recent discovery even revealed that Mars can produce its own form of mini-lightning, which adds another layer of risk for humans. But on a planet with almost no atmosphere, no rain, and no thunderstorms, that shouldn't be possible. So, what's really going on? And what other unobvious dangers would future humans face there? This video brings those pieces together using the latest research and discoveries. Let's take a closer look. At first glance, Mars doesn't come across as a truly alien world so much as an incomplete version of Earth, smaller, colder, and stripped down, but built from many of the same parts. It is roughly half Earth's diameter, yet its surface still carries recognizable features. Long valleys carved into the ground, towering volcanoes, broad plains, and bright polar ice caps that expand and shrink with the seasons. Gravity on Mars is weaker, at roughly 38% of Earth's, allowing a person to move more easily and jump higher. The planet lies farther from the sun, which makes it colder overall, though sunlight remains plentiful and time still follows a familiar rhythm. A Martian day lasts just under 25 hours, only slightly longer than Earth's, and the planet's axial tilt is similar to our own. As a result, Mars experiences genuine seasonal cycles with temperature changes and shifting ice at its poles. So initially, Mars does appear surprisingly Earth-like, with near-Earth days, seasonal cycles, and polar ice. But this feeling of familiarity disappears once you look more closely. The lower gravity that seems easy to live with also made it harder for Mars to keep a thick atmosphere. Over billions of years, much of its air drifted away into space, leaving only a thin layer that provides little warmth or protection. Mars is also farther from the sun, which makes it colder. Because the planet is smaller, it lost its internal heat early on. Without enough internal energy, Mars could not support long-lasting geological activity like Earth's moving tectonic plates. Today, Mars may look like Earth in some ways, but it does not work like Earth at all. Mars's color reveals more differences. The planet is famously red, and that is accurate, but incomplete. Martian rocks contain iron, much like rocks on Earth. Over time, that iron reacted with oxygen to form iron oxides, essentially rust. On Earth, processes like rainfall, oceans, erosion, and tectonic recycling continually reshape the surface, burying and breaking down oxidized material. Mars lacks those active systems. Once iron oxidized there, it largely stayed in place. More importantly, that rust didn't remain locked inside solid rock. It broke down into extremely fine particles. This dust is what truly defines Mars's appearance. It is pervasive, lightweight, and easily mobilized. It blankets the ground, settles into depressions, clings to rocks, and is frequently lifted into the atmosphere. From orbit, and especially from Earth, we are mostly seeing this thin veneer of oxidized dust rather than exposed bedrock. Up close, Mars is not uniformly red. Its surface includes shades of brown, tan, gray, and even gold. But the dust smooths these variations into a single dominant color when viewed from afar. The planet's winds, though weaker than Earth's, are highly effective under Martian conditions. Lower gravity and a thin atmosphere mean it takes surprisingly little force to lift fine particles. Dust devils regularly sweep across the landscape, and larger storms can cover vast regions of the planet. Over long periods of time, these constant movements reshape the surface. Dust is stripped from some areas and piled onto others, slowly revealing rock in one place while burying it elsewhere. And yet, the surface shows clear signs of something that shouldn't be possible on a dead planet. Across its surface are dry river valleys that split and wind, just like river systems on Earth. There are broad lake basins with defined shorelines, floodplains built from repeated overflows, and fan-shaped deltas formed where rivers once slowed down and dropped their sediment. These features follow patterns that, on Earth, are shaped only by flowing water over long periods of time. Some of the most compelling evidence comes from ancient craters that once held lakes. In these basins, scientists see clear signs of water entering and leaving through river channels, suggesting the lakes were stable rather than short-lived. In several places, sediment is arranged in layered stacks that could only form if water returned again and again. This rules out the idea of a single catastrophic flood, and instead points to a climate where liquid water persisted long enough to reshape the landscape gradually. On an even larger scale, parts of Mars's northern hemisphere may once have been covered by a vast ocean. The terrain there is lower and smoother than much of the rest of the planet, and beneath the surface lie buried layers that resemble coastal deposits on Earth. These structures are hidden under dust and sediment, which protected them from erosion long after surface features faded. The idea of a northern ocean has been debated for decades, but recent subsurface measurements have strengthened the case. If such an ocean existed, it would have covered a significant portion of the planet. The question then is what caused this watery world to disappear? The answer is that Mars is smaller than Earth, and as mentioned earlier, smaller planets lose internal heat more quickly. Early in its history, Mars had a hot, active interior that generated a global magnetic field. Like Earth's magnetic field today, it acted as a protective shield, deflecting charged particles from the sun. As Mars cooled, that dynamo weakened. Eventually, the magnetic field collapsed. With its shield gone, Mars became exposed to the solar wind. High-energy particles began interacting directly with the upper atmosphere, slowly stripping it away. Lighter gases escaped first, but heavier components were lost over time as well. As the atmosphere thinned, surface temperatures dropped, and liquid water could no longer remain stable. Rivers dried up, lakes vanished, and water either froze into the ground and polar regions or escaped into space. Once the atmosphere fell below a critical threshold, Mars could not recover. The planet crossed a one-way boundary, transforming from a world that could support liquid water into the cold, hostile environment we see today. Now, here's the uncomfortable part. Everything Mars lost is exactly what life needs, which means the most important question is whether life ever existed there. Early in its history, Mars met many of the conditions we associate with a habitable world. Liquid water was present on the surface, energy sources were available, and the basic chemical building blocks of life existed at the same time. If life ever arose there, it was likely simple and microscopic, resembling the microbial life that dominated Earth for billions of years. The Martian surface today is harsh and exposed. With little atmosphere and no global magnetic field, it is constantly bombarded by radiation, which makes long-term survival difficult. Beneath the surface, however, conditions change dramatically. Underground environments offer more stable temperatures, natural shielding from radiation, and the potential to preserve traces of ancient, more hospitable conditions. For this reason, scientists focus their search on sedimentary rocks and buried layers rather than the exposed surface. These materials form in the presence of water and can lock away chemical signatures for immense spans of time. If life once existed on Mars, these protected environments are the most likely places to find evidence it left behind. Another intriguing clue is methane. Small and irregular amounts of methane have been detected in the Martian atmosphere, appearing and disappearing over time. On Earth, methane can be produced by living organisms, but it can also form through purely geological processes. On Mars, the measurements don't fully agree, and its behavior remains a mystery. Now, with water and protection gone, the forces that remained were left to run unchecked. And now Mars isn't just extreme, it allows things to form that shouldn't be able to form anywhere else. Take Olympus Mons. It is the largest volcano in the solar system, rising about 3 times higher than Mount Everest and spreading so wide that its summit disappears beyond the planet's curvature when viewed from the base. Its enormous size is not accidental. On Earth, moving tectonic plates carry crust away from volcanic hotspots, cutting off eruptions and creating chains of smaller volcanoes. Mars has no such plate motion. Once magma found a pathway to the surface, it kept erupting in the same place for millions of years. Lower gravity added to the effect, placing less stress on the growing mountain and allowing Olympus Mons to rise to an almost absurd scale. Equally dramatic, but shaped by different forces, is Valles Marineris. This vast canyon network stretches thousands of kilometers across the planet and plunges far deeper than any canyon on Earth. It was not carved by flowing water like the Grand Canyon. Instead, it began as Mars's crust was pulled apart. The immense weight of nearby volcanic regions strained the surface, causing it to fracture and collapse. Over time, landslides and minor erosion widened those cracks, but the canyon itself remains a structural scar, evidence of a planet under stress. Extremes are just as common in Mars's atmosphere and weather, and this is where Mars becomes much harder to live on than it looks. Mars has an atmosphere so thin that standing on its surface would feel almost like being in a vacuum. Air pressure there is less than 1% of Earth's, offering very little protection. And again, even so, this weak atmosphere can create dust storms large enough to cover the entire planet. Once dust gets into the air, it starts to change how the planet behaves. The dust absorbs sunlight and warms the atmosphere, which shifts wind patterns and lifts even more dust. This cycle allows storms to grow larger and last longer. The danger isn't strong winds knocking things over, but how these storms block sunlight and change temperatures for weeks or even months. Temperature changes on Mars are also extreme. With so little atmosphere to hold in heat, the surface warms quickly during the day and cools just as fast at night. In some places, temperatures can change by dozens of degrees in a single day. Warm afternoons can quickly turn into freezing nights, making Mars one of the most temperature-extreme planets in the solar system. And beneath these obvious dangers, Mars hides a quieter, stranger threat. What scientists discovered next challenged one of their most basic assumptions about Mars. For a long time, Mars was treated as electrically quiet, and by everything we understood about electricity, it should have been. On Earth, lightning forms inside tall storm clouds filled with rain, ice, and rising warm air. Mars has none of that. It has no rain, no towering thunderstorms, and an atmosphere so thin that electrical sparks shouldn't form easily. For a long time, this made Martian electricity seem unlikely. Scientists thought it might be possible in theory, but not something that would actually happen often enough to be observed. But that assumption turned out to be wrong. Mars has its own kind of mini lightning, and it's nothing like Earth's. On Mars, electrical activity happens much closer to the ground. The planet is covered in extremely fine dust, and that dust behaves in unusual ways. When dust grains collide and rub together, they can build up electrical charge. On Earth, moisture in the air helps drain that charge away. Mars is effectively dry, so the charge lingers, especially when dust is moving quickly. Dust devils provide the perfect conditions. They form easily on Mars as spinning columns of dust that can rise hundreds of meters high. Inside them, particles are constantly crashing into one another. As the charge builds up, it eventually needs a release. And when it does, it doesn't look like lightning at all. When the electric field inside Martian dust clouds grows strong enough, it releases in quick, sharp bursts. These aren't dramatic lightning bolts streaking across the sky. They're tiny sparks, only centimeters long, closer to a static shock than a thunderstorm strike. For the first time, scientists have directly detected these discharges on Mars. They didn't see flashes of light. They heard them. Instruments on the surface recorded faint crackling sounds and electromagnetic signals as dust devils passed nearby. The patterns matched exactly what small electrical sparks would produce. This wasn't a single lucky detection. Over time, dozens of these events were recorded. And once you realize that, a much bigger question follows. Electrical discharges can drive chemistry. When sparks pass through the atmosphere, they can create highly reactive molecules. On Earth, lightning helps produce compounds like nitrates. On Mars, similar processes may create oxidizing chemicals that break other molecules apart. This connects directly to something we talked about earlier, methane. One possible explanation to its strange behavior on Mars is that it is actively getting destroyed. Electrical discharges in dust storms may create reactive chemicals that break methane apart quickly, which helps explain why it's so hard to track and why measurements don't always agree. The same process could affect other organic molecules too. Mars is already hostile to complex chemistry. Radiation damages it. Oxidizing soils break it down. Add electrical activity into the mix and the surface becomes even less forgiving. If organic compounds exist or once existed, these sparks may be helping erase their traces near the surface. There are practical concerns too. Even small electrical discharges can interfere with sensitive equipment. Instruments designed for cold and dust still have to survive static buildup, electric fields, and repeated sparking nearby. For robotic missions, that's an engineering challenge. For humans, it's another environmental hazard layered on top of many others. Not dramatic enough to kill you outright, but persistent enough to matter. Dust devils, once thought of as mostly harmless whirlwinds, start to look more like moving electric generators. They scrub the surface, rearrange dust, and now we know they can spark as they go. If humans ever go to Mars, it'll be far less forgiving than it looks. But if Mars is such a hard place to survive, the obvious question is why we keep coming back to it. The answer isn't that Mars is good, it's that compared to the alternatives, it's the least bad option. The Moon is closer, but it's harsher in key ways. Its gravity is far lower, which poses risks for long-term human health. Its day-night cycle is extreme, with weeks of daylight followed by weeks of darkness, and it offers fewer obvious resources to work with. Mars, by comparison, has a day that feels familiar, gravity that's low but not negligible, and an environment that, while hostile, can at least be planned around. Mars also has something the Moon largely doesn't: usable resources spread across the planet. Water ice exists not just at the poles, but in mid-latitudes, potentially shallow enough to access. Water isn't just for drinking. It can be split into oxygen and hydrogen, which means air to breathe and fuel to burn. Mars also has a carbon dioxide-rich atmosphere that can be processed. This is why Mars keeps winning on paper. It's far away, dangerous, and unforgiving, but it offers a path towards self-sufficiency that the Moon struggles to match. That said, distance changes everything. Mars is so far that it's isolating. A trip there takes months, and once you arrive, help is not on the way. Communication delays mean conversations with Earth happen minutes later, not in real time. If something goes wrong, crews can't rely on instant instructions or quick rescues. Every decision has to be made locally, with limited backup. That isolation is part of the cost of choosing Mars. Even reaching the surface safely is its own ordeal. Landing on Mars is one of the hardest things we try to do in spaceflight. The problem is the atmosphere. It's thick enough to cause intense heating during entry, but too thin to slow a spacecraft down on its own. Parachutes help, but only up to a point. Rockets are needed, but they have to fire at exactly the right moment. All of this happens automatically, in minutes, with no chance for human intervention. This is why so many missions have failed. Small errors stack up quickly, and Mars doesn't forgive them. Every landing uses a carefully tailored system, and even then, success is never guaranteed. Mars is easy to reach, and brutally hard to touch. When things do work, though, the payoff matters. We now know that machines can pull oxygen from the Martian atmosphere itself. That's a huge step forward, but it doesn't make Mars safe. It doesn't fix radiation, cold, dust, or isolation. What it does is reduce how much we have to bring with us. It makes future missions more realistic, not easy. That realism is important when talking about terraforming. Turning Mars into a second Earth is a popular idea, but it falls apart under scrutiny. Terraforming would require thickening the atmosphere, warming the planet, and keeping it stable over enormous timescales. Mars simply doesn't have enough accessible carbon dioxide left to do that. Even if we released everything available, it wouldn't be enough, and that's before considering the centuries or millennia it would take, or the ethical problem of changing a planet we don't fully understand. Mars isn't a backup Earth or a simple destination waiting for us. Habitability depends on balance, shielding, and time, not just distance from the sun. The more we learn about it, the clearer it becomes that surviving on another world is harder than we imagine and easier to lose than we expect.